So, if you're in the life sciences, you spend a lot of your time working with things you can't actually see, right? But you still have to count them? How in the world do you do that? Well, that's exactly what we're going to tackle today. We're diving into a concept that is, and I mean this, the absolute backbone of every lab, the mole. It's so much more than just a number. It's the key to making sure your experiments are precise and repeatable.
I mean, think about it. It's a real puzzle, isn't it? You can't exactly line up atoms and count them one by one. So how do we possibly bridge that gap between the totally invisible world of molecules and the world we live in, with scales and beakers? Luckily, chemists came up with a pretty brilliant solution.
All right, here's the game plan for our journey today. We're going to start with this idea of a chemist's dozen to really understand what a mole is. Then we'll connect that idea to something we can actually weigh, mass. After that, we'll get into solutions and concentration, and finally we'll wrap up with a super practical lab skill, dilution.
Okay, first things first. Let's get to the heart of it. What exactly is a mole? Probably the easiest way to get your head around it is to think about a word you already use all the time. A dozen.
You know that a dozen eggs is 12 eggs. Simple. A mole is pretty much the same idea. It's just a convenient name for a specific number. The only catch? This number is, well, it's astronomically large.
And here it is, 6.022 times 10 to the 23rd power. That's Avogadro's number. We're talking about a 6 followed by 23 zeros. It's a mind-bogglingly huge number. But it has to be, right? Atoms are so incredibly tiny that you need a truly immense number of them to get a sample that you can actually see and work with in the lab.
So here's the main takeaway. A mole is just our standard unit for counting particles. 1 mole of anything, whether it's hydrogen atoms, water molecules, or sugar crystals, is always 6.022 times 10 to the 23rd particles. And you know what? That consistency is its superpower.
But let's be real, we can't count individual atoms. It's not practical. What we can do, though, is weigh things. So the big question is, how do we connect this gigantic number to something we can actually measure on a lab scale? The answer is all about mass.
This right here is our bridge, molar mass. It is simply the weight of exactly 1 mole of a substance. And here is the really cool part, the thing that makes it all work so beautifully. The molar mass in grams is the exact same number as the atomic mass you see on the periodic table. So for water, H2O, its atomic mass is about 18 AMU. That means 1 mole of water weighs, you guessed it, 18 grams. It's that simple.
And this simple little formula is the key that unlocks everything. If you know the mass of the stuff you've weighed out, and you know its molar mass, you can figure out the exact number of moles you have. Trust me, this is a calculation you are going to use constantly in any lab setting.
Now, most of the time, especially in biology, we aren't working with pure powders. We're working with solutions, something dissolved in something else, usually water. And that means we need another way to describe what we're working with, concentration.
To put it simply, concentration just tells you how much stuff, the solute, is dissolved in your liquid, the solvent. Is it super crowded with solute particles, or are they spread really far apart? Being able to quantify this is absolutely crucial for getting consistent, reproducible results in your experiments.
Okay, but here's the thing. There's more than one way to talk about concentration. Different situations are going to call for different units of measurement. So let's take a quick tour of the most common ones you're going to run into in the lab.
First up, we have the heavyweight champion, especially in biochemistry, molarity. You'll see it written as a capital M. And it's all about one thing. How many moles of your solute are dissolved in a final volume of 1 liter of the entire solution?
The formula itself is super straightforward. Molarity is just the moles of your solute divided by the total volume of the solution in liters. So when you see a bottle on the shelf that's labeled 1M NaCl, you know instantly that every single liter of that solution has exactly 1 mole of sodium chloride in it. Next up is its close cousin, molality. And notice it's got a lowercase m. It's really similar to molarity, but there's one critical difference. Molality is based on the mass of the solvent, not the total volume of the solution. So the formula for this one is moles of solute per kilogram of the solvent. Now, this distinction might seem tiny, but believe me, it has some really important practical consequences, especially when your experiments demand extreme precision.
All right, let's put them side by side to really see the difference. Molarity uses the volume of the whole solution. Molality uses the mass of just the solvent. So why does this matter so much? Well, think about it. Volume can change with temperature. Liquids expand when they get warm, right? That means molarity is actually temperature dependent. Mass, on the other hand, never changes. That makes molality the go-to choice for experiments where the temperature might fluctuate, and you need rock-solid precision.
Of course, there are other ways to measure concentration. You often see mass percent, which is just a simple ratio of the solute's mass to the total solution's mass, super common for things you'd buy in a store. Then there's parts per million, or ppm, which is perfect when you're dealing with incredibly dilute solutions, like measuring trace contaminants in water. And finally, you've got mole fraction, which compares the moles of one ingredient to the total moles of everything in the mix. The best unit always depends on what you're trying to do in your experiment.
Okay, so we've got our core concepts down. Now, let's talk about the single most common application for all of this stuff. Taking a really concentrated stock solution and diluting it down to a working concentration that you can actually use for an experiment.
I mean, it's way easier and a whole lot more accurate to make one big batch of a concentrated stock solution and then just dilute a little bit of it whenever you need it, instead of trying to weigh out teeny tiny amounts of powder every single time.
And the whole process is governed by this beautifully simple and powerful equation, C₁V₁ equals C₂V₂. It's your best friend in the lab. It works because the amount of solute you start with is the same amount you end with, it's just floating around in a bigger volume of solvent. C₁ and V₁ are your starting concentration and volume, and C₂ and V₂ are the final concentration and volume you're trying to make.
Let's actually put this into practice. Imagine we need to make 100 milliliters of something called solution X. We have 3 different stock solutions, and we're just going to use C₁V₁ equals C₂V₂ for each one. We just rearrange the formula to solve for V1, which is the volume of stock we need. For the tris, the math tells us we need 2.5 ml. For the NaCl, we need 2 ml, and for the EDTA, we need 5 ml. So we carefully measure and combine those volumes. That's 9.5 ml total. And to finish, we add exactly 90.5 ml of water to get to our target of 100 ml. And just like that, you've done one of the most fundamental tasks in any life sciences lab.
You see, these calculations aren't just some abstract math problem, they are the absolute bedrock of accuracy and reproducibility in the lab. Understanding the mole, grasping concentration, and mastering dilution. This is what gives you control over the invisible world of your experiments. And in a field where a single drop can literally be the difference between a breakthrough and a failure, that level of precision, well, that's everything.